In this lecture, we'll overview the electron beam lithography technique. In the previous lecture, we went through the photolithography technique and its limits. Photolithography resolution is mostly limited by the diffraction of the UV light or UV radiation. In the contact mode or soft contact mode, it is limited by the near field diffraction, and in the projection mode, it is limited by the far field diffraction. In this case, what we are doing is we are using high energy electron beam to write nanoscale patterns. So here we are not limited by the wavelength of the electrons. We are mostly limited by the resist properties and also the quality of the electron beam optics. Okay. Here this is a schematic of electron beam machine, which is also a microscope. It's the electron beam microscope. We have a source of electron. We extract the electrons from the source using electric field, using some electrodes. Okay, and there are focusing mechanisms which actually can focus the electron beam onto substrate. And there are also coils, which are scan coils, which you can use to raster the beam onto the substrate and also write whatever the feature you want using the beam. And apart from that, there are also the components or mechanism where you can take the image of the substrate, either using the backscattered electron or the secondary electrons. The advantage of using electron beam machine is mainly the resolution. The electron beam microscope and this electron beam machine can image and also write with very high resolution of the order of a few nanometers. The modern day machines can go down to few nanometers in imaging resolution. But the writing resolution, as I mentioned, is mostly limited by the properties of the resist that we use. Okay, the polymer substrate or the resist that we got on top of the substrate. Okay. Here, this is a picture of a modern day electron beam writer, which you would find usually in a lab or institute atmosphere. Now, let us quickly look at what are the effects of the electron with the interaction effects of electrons with the substrate. Okay, so here is a primary electron beam with a high energy electron beam of the order of few tens of kilo electron volt. So you can have these beams with energies like maybe 15 to maybe 100 kilo electron volt. That is typically the energy used for writing these patterns. So let's say 15 kilo electron volt to something 100 kilo electron volt. That is what these electron beam machines come with. Okay. So when such a high energy electron beam falls on the substrate, you are going to have a few different effects. You can have these electrons backscattered. You can have secondary electrons produced from the primary beam. And there are other effects such as cathodoluminescence, OJ electrons, X-rays, which are not really relevant for our discussion on lithography here. Okay. So lithography mostly happens with the secondary electrons. Okay. And here this detector also takes the image using the secondary electrons. These secondary electrons are low in energy and it's emitted from the surface mostly. So that will have the characteristics of substrate is mostly suitable for observing the surface topography. And the number of secondary electrons and its characteristics depends on the incident angle and also the primary beam electrons and the surface interaction and nature of the surface also. And apart from all this, there is also a transmitted electron beam, which you can get whenever the substrate is really, really thin, which will allow the electrons to go through That is what is used in transmission electron microscopes. But this is a scanning electron microscope where you are getting the image using the secondary electrons or the backscattered electrons, and you are using this machine to write the pattern using the secondary electrons. So let's look at what limits the resolution. So we just now discussed that the spot size or the feature size that you can get with the imaging feature or the spot size that you can get is approximately like few nanometer. Okay, spot size is like maybe 2 to 5 nanometer. That's what you can get. Okay, now let's look at what limits the resolution. Okay. So mostly in lab atmosphere, you can get patterns down to 20 nanometer without a lot of effort. But pushing below 20 nanometer requires a lot of extra care. Okay. So most of these resolution issue come from the lateral diffusion of the secondary electrons. Lateral diffusion of the secondary electron and also the forward scattering characteristics. The forward scattering deflect the primary beam. The primary beam is here. Okay, this is the primary beam. The forward scattering deflects this primary beam. Okay, and also generate the secondary electrons here, which are shown by these thin small arrows. And these are much lower in energy, and these are responsible for exposing the resist or responsible for the chemical chain that happens in the resist. And these secondary electrons are the one which does the job for us in the lithography process. So they are generated and mostly travels in a direction which is perpendicular to the primary beam. So they travel somewhat laterally. Okay, and they also diffuse laterally. So rather than just causing the chemical change at the spot size, this diffusion of these secondary electrons will have an effect of widening the feature size. So if the beam size is say 2 nanometer, but the secondary electron propagates laterally to few more nanometers. Okay, so the effective area of the resist which is getting affected will be like maybe another few more nanometers. Okay, if you define 2 nanometers as spot size, eventually you probably will be getting like 6 to 7 nanometer as the feature size. You have to add few more nanometers to that. So it's not just the area where the primary beam has been bombarded, also a circumference or an area around it will get exposed, that is by the secondary electron. And of course this diffusion characteristics of the secondary electron will, if it further diffuses, that also can broaden the feature. Okay, so there are a lot of these parameters which will play into while deciding the feature size when you do lithography. Though the spot size is 2 nanometer, lithography mostly is decided by the characteristic of the resist, because the diffusion characteristics of secondary electron is completely decided by the resist. Okay. And of course, there are also factors which play, because how many secondary electrons are produced and how much backscattered electrons are produced. All this will have an effect. Those depends upon the interface between the resist and the substrate. Okay. And the third limiting factor is the resist swelling by the developer. So when you post-process it or when you develop this, you will dip this substrate into some solvent that actually can cause a little more chemical change, further chemical change, and kind of swelling effect that will broaden or soften the feature that you have written. Okay. So eventually, what is responsible for the feature size is mostly the characteristics of the resist and the scattering mechanism. It's not the primary beam. That is the take-home message. Okay. There is a interesting contrast between the photolithography and the electron beam lithography. The photolithography uses photons which are not charged particles, whereas electron beam lithography uses electrons which are negatively charged. So, photolithography doesn't really care about the polarity or the nature of substrate. But for conducting electron beam lithography, you have to keep the substrate electrically neutral, else you will have charge accumulation which is going to interact with the oncoming electrons. Okay, and there will be a repulsive interaction and you will not get a good pattern, and it's almost impossible to write anything useful if the substrate gets charged, and you cannot also get an image either. So the charging effect is a huge issue. So you cannot directly write onto any substrate which is highly insulating or even semi-insulating, okay, because the charging effect is going to affect your resolution and also the pattern feature. So you need to have some kind of mechanism to remove this charge as soon as it falls on the substrate. Okay. So, but generally, this most of the resistors are actually insulating. They are polymers. Okay. But here, the thickness of the resist is really small. It's almost like a few hundreds of nanometer. So the electron beam, the primary electron beam which falls on, will directly interact with the substrate which is assumed to be conducting. Okay, so the charging effect is not a huge issue when you use thinner thinner polymer. Okay. Okay. Now, but insulating substrates such as glass or quartz, okay, or even highly resistive silicon, okay, or gallium arsenide, okay, these wafers or these materials can cause charge buildup and the beam will get deflected and also will result in pattern distortion. So what generally is done in such situation is you can have some kind of a conducting layer on top or beneath of the resist. So you can put a really thin layer of say metal such as aluminum, titanium or chromium or sometimes gold on top of the resist. Okay, you bake the resist, you coat the resist, bake the resist, and there is a process which which are very simple. But you coat the resist, then you bake it at a certain temperature, which is prescribed by the resist manufacturer. Then after that, then the resist is prepared for the exposure. Okay, and after that, you can coat a very thin layer of gold, like few nanometers of gold or chromium, titanium, or any other metal, which you can easily remove. Okay, this thin metal will not pose any hindrance to the electron beam. So it will pass through, it will be transparent, it will pass through, but the charge neutrality will be taken care. For the charge grounding thing will be taken care by this metallic nature of the substrate. Okay, so usually lighter metals are preferred because the heavier elements can actually interfere with the beam and cause more backscattering. Okay, so the forward scattering will not be much affected if you have lighter metal. So that is the reason aluminum or titanium or chromium is preferred. Okay, and these except gold, this titanium, aluminum, or chromium can easily be removed using diluted hydrofluoric acid after the processing without affecting the resist. So you have to remove it before you develop it. So you can dip it in hydrofluoric acid. You can get this layer of chromium or aluminum or these things removed. Then you can do your normal developing. That is the process. Okay. Here we have few representative images of electron beam lithograph structures. Here this is an emblem of the Institute ISR Thiruvananthapuram. You can see the overall scale is 30 micrometer. So if you walk down through this line, the tip of this will be like a few, maybe like 100 nanometer or in that range. Okay. And this we already have seen. This is also done by electron beam lithography, and the feature size, the smallest feature size is like 6 to 7 nanometer. The picture here shows a image which is done with a combination of electron beam and photolithography. Okay. The larger structures that you're seeing here, those are done by photolithography, and the small structure in the middle, this yellow or golden shape, golden colored region, a magnified view of this structure is given here in this picture, in this image. So this is center here. Okay. So what you do here is you write the larger structure with the photolithography and the smaller structure with the electron beam lithography. So there are two lithography stages. You finish the first lithography, do the metallization, then take the sample and repeat the process but using electron beam lithography. Okay. So here what you are seeing is the smallest feature here is like less than 100 nanometer of size. These gates, these are surface gates. This is like less than 100 nanometer, close to 60-70 nanometer. That's what we have in this picture. Okay. And the overall size scale is here. Okay. Scale bar is 1 micrometer. Okay. And what you're seeing in this picture is nano machines, nanoscale gears, which are done by electron beam lithography plus further processing such as metallization and etching. Okay, this is done at Sandia Labs. And so this slide telling you how powerful the electron beam lithography is, but the downside is the substrate choice are limited and the throughput is really low because this is a serial processing. So you have to write structure by structure. You cannot expose parallelly the features down all the wafer, the complete wafer at once. Okay, because you have to write, it's a writing process, whereas other one is a exposing process. You have a mask and you expose all the region at once. Here you write the feature one by one. So this is not really compatible with ultra high throughput process site. You don't have as much yield as photolithography process, Okay. So now we have reviewed the photolithography process in the previous class and the electron beam lithography process in this lecture. Okay. Generally, the other two techniques or processes which accompanies the lithography is metallization, and the second one is etching. Okay, so let's look at this process also very briefly for completeness. When you finish the lithography either with electron beam or with light, you will generally end up with 3 profiles after developing. Okay, you have something called an undercut, where you have a wider region close to surface and a narrow region or a neck kind of region at the top surface, where this dark region is the photoresist or electron beam resist, and this is the substrate. Okay, this is the substrate. This profile is called undercut. Okay, this is also called lift-off profile. You will come to know very soon why this is called lift-off profile. Okay, and this is called overcut. This is just like you have wider region on the top and a narrow region on the bottom, and it's a vertical profile, but the width is more or less same after you develop it. So now imagine that in each of this case you are going to do a metallization. Okay, after lithography, what you would do is you will deposit some metal, which will act as a gate, electrode, or ohmic contact. Okay. Now, when you deposit metal, Let's consider in the second case where you have overcut profile. Okay, in the overcut profile, what happens? Okay, when you have in this profile, when you are in this profile, the metal will get deposited throughout all this region when you do metallization. Okay, it will be continuous film. So metal comes from metal atoms come from here, from a source which is called thermal evaporator or electron beam evaporator, or could be from a sputtering source. Okay, it will get deposited everywhere. Now, next step is lifting off. Lifting off means it is the stripping the resist, where you will lift off you will dissolve the resist which is on either side here. Okay, and you eventually you want to end up with only the metal piece where it is exposed. Okay, that's what you want. But in this case, since it's a continuous film, the lift off will not be clean, because lift off needs something like an undercut profile where you have a wider bottom region, something like this, so that when you deposit metal, you get breaks or a discontinuous film, so that it's easy to peel off this region and this region. Okay, so that you will eventually end up with only this piece of metal on the surface. So since you have metal coated on the side walls in a overcut profile, it's a continuous film of metal when you look from the top. So when you try to lift off the metal which are on the resist side, which is not developed, but either all metal will get lifted off, or some of the metal piece will stay there, so that you will end up getting a distorted or continuous pattern. Wherever you want break, you won't get it, because you will have pieces of metal left and pieces of metal broken where you wanted. And all these effects, undesired effects, will be there. So what you need for a clean lift off is something called an undercut or lift off profile, which is something like this. Okay, but we want more cave-like feature towards the bottom. You want an undercut, so that when you deposit metal, you get breaks, so that the metal film is not really continuous. Okay, so generally this undercut profile is obtained by something called a bilayer resist. The vertical profile is also fine, but if there is a small angle when you deposit metal, then you can get coated metal on the sidewalls also, which is not desirable. So vertical profile is also fine as long as the metal deposition is perfectly normal to the substrate, so that you have break in the film at the edges of the resist, or sidewalls of the resist. But usually this undercut profile are obtained by using something called a bilayer resist scheme, where you have a weaker bottom layer that will undergo more chemical change, and it will give you a cave-like feature. Okay, something like this. Okay, so that naturally the metal which is deposited, which is here, will get broken at the side. So there are breaks here, or there are breaks here, so that the lift off will be clean. So when you lift off it, so when you strip the resist, all this portion will get disappeared. Okay, and you will eventually end up with only this piece here, as shown here. You will have this one. But if you have perfectly vertical side walls, you can get a thin film of metal coated on the side that is going to give you something like a fan shape at the edge. That is also not really desirable for these devices, because these are like really pointy structures which actually also going to affect the electrostatics near the region, because these gates or these structures will be used to apply electric fields or run currents into it. So this can actually affect your performance of the device. So what is really desirable is this structure, which generally is obtained by using an undercut profile. Okay, having an undercut profile or lift off profile. So most of this lithography, especially high resolution lithography, plain lithography, needs bilayer resist scheme. So you have a bottom layer which is slightly weaker, and the top layer is going to define your define the resolution. Okay, but bottom layer will help you to lift off it correctly. Okay. Now let us very quickly overview the metallization process. Metallization is a very simple process to understand. What you have is you have a source which is going to look like something shown, like something shown here. It's like a boat or a basket, which you can, where you can keep the metal that you want to put on the substrate. Then you heat it using a high current running through this basket. Then it's going to glow like this, as shown here. Then this metal will evaporate and get deposited on the substrate. So assuming that most of these metal atoms travel perfectly normal to the substrate. And this is a picture of a simple machine which is called thermal evaporation. This thermal evaporator, and this process is called thermal evaporation. This is how you keep the material inside, and this is how it's going to look like when you do the evaporation. And there is a limit what kind of metals you can do thermally. We can perform thermal evaporation, because this depends upon the melting point of the metal. So if you have metals with a very high melting point, such as molybdenum or titanium or other like palladium, you will resort to a similar technique which is called electron beam evaporation. There you don't use the direct current or ice cold arc heating to evaporate the metal, just like as shown here. What you do is you will use electron beam, energy from the electron beam. A small electron beam is going to bombard the basket where you are going to keep the material, and that will get evaporated from there with that energy. Okay, so that is the technique which we use when you have refractory metals or metals with high melting points. And another technique which generally used for metallization is sputtering. There are various different versions of this sputtering. It's called plasma sputtering, where you have a glow discharge plasma inside, and you have a material which you want to coat, and the substrate where you want to coat it. So this plasma is biased so that the metal, once it is sputtered out, will eventually get deposited on the substrate. So this is an isotropic process. What I'm trying to say is the metal which will get released from this target and go deposit on the substrate, deposit in all the angles. It's a plasma. Okay, so it also will coat the side walls of the resist. So using plasma sputtering, it's very hard to get a very good lift of profile, because the metal film also will get caught on the side walls, as we discussed here. So lifting off is not really easy when you deposit metal using sputtering. Okay. Now a very quick look at the other process, that is etching. Etching is the removal of material, but metallization is the addition of material. So once you finish the lithography, you will have a profile where you don't have the resist in the middle, somewhere in the middle, and you can load this substrate into a machine called a plasma etching or dry etching system. There are various versions of this dry etcher. There are DC, RIE, RF plasma, all kinds of machines are there, but we are not going to go in details here. So what you have here is energetic ions in the plasma, which is going to bombard on the exposed region and sputter the material out, and you are going to get a pit. There are again variations of this etch profiles. You can have perfectly vertical, completely anisotropic profile, and you can have a profile which looks like a boat shaped here, and you can also have isotropic profile. Generally, the plasma etching gives anisotropic etch profiles where high aspect ratio is required. But you can also do this etching chemically using wet chemical etching, where the chemical reaction will remove the material. It'll convert some, it'll break some bond, it'll make some bond, and you can also dissolve it in certain solvents. Okay. So when you do chemical reaction to do etching, this is also called wet chemical etching, then that is not really directional. Okay. So you will get more or less a uniform etch profile. It will etch in all the directions uniformly. So you will not get this high aspect ratio profiles using wet chemical etching. If your work require structures with a really high aspect ratio, you always have to go with the dry etching. And there are dry etching techniques, and there are also variations in the dry etching technique which will give you more and more or better and better aspect ratios. Okay. So that is the story about etching. Now we have reviewed the lithography techniques, the metallization technique, and also the etching technique. Okay. Now let's go through a complete device fabrication process flow. Okay, a step-by-step process step by step, starting from the bare wafer down to the final device. Okay, so this is what generally used for most of the gated devices that we discuss in the rest of the lectures. Okay, so you have a substrate. Assume that this is a silicon substrate for the time being. A silicon germanium 2-dimensional electron system. You assume that. Okay. And the typical dimensions are shown here. And one of the first steps that you would do is you will remove the material or remove the 2-deck wherever you don't want it. So you will etch down regions where you don't want the 2-deck by photolithography. So once you etch it down, you will get a profile which looks something like this. Okay. So wherever the darker region, wherever you have the darker color, you don't have any 2-dimensional electron gas there. You have etched down the wafer a little bit. Okay. Now, by this process, you have defined the path for electrons. Okay. You can come and center region here is the active region. And next process would be you need to define ohmic contact to this region because you have to run currents and measure voltages. So you have to inject electrons. So for that, you need ohmic contact. These contacts inject the electrons into the channel, which is the 2-dimensional electron gas in the middle. Surface, then you have a stack, right? You have surface, you etch down wherever you don't want it, but then you also need to inject electrons into the 2-dimensional electron system. What you do is you diffuse some dopants in this region, either by ion implantation, or you can also use some technique called alloying technique, where you make those regions degeneratively doped, okay, from top to bottom, top to the well. So this region will act like the contacts or ohmic contacts or metals, which contacts the 2-dimensional electron system in the middle. Then the next step would be we need to define the larger gauge structures which are defined by photolithography. Okay. And again, these features are pretty large, like a few micrometers are the smallest feature here. These are done by photolithography. And eventually, you need to define really small structure, which is in the few tens of nanometer scale in the middle. That is done by electron beam lithography. So after this step, you actually draw this small feature which you are shown here, the enlarged SEM picture, the scanning electron microscope picture is given here. This is basically whatever you are seeing here, that is this picture. Okay. So that is done by electron beam lithography. So you finish all the large scale structure by photolithography and associated process such as metallization or etching. So you have etching, this is an etching stage, and rest of them are actually metallization stage. Then there are annealing stages in the middle. Okay. Then you transfer the wafer from the process flow of photolithography to the electron beam lithography. Okay, here using electron beam lithography, you finish and define the really fine gates, where these gates are like few tens of nanometer, like 30 to 40 nanometer. 300 nanometer scale is here. Okay. So this slide shows a typical step-by-step process that one need to follow to get a gated device. This device eventually would work as a electrostatically confined quantum dot structure. So when you energize all these gates, you will get a small puddle of electron in the middle, confined electrons in the middle, and you also will get some thin channel here. These are quantum point contacts, which you will learn in one of the coming modules. Okay. All right. So in nutshell, during this lecture and the last lecture, we reviewed the sample fabrication technique, especially with a focus on what generally is done in a university or institute atmosphere in the research lab. Okay. And this is no way related to what is being done in the industry. That is a much larger scale process, which are not really affordable by normal university or institutes. All right.